Last time we were looking at a result for gradient flow on the empirical risk under the exponential loss. So theta t dot was the negative, and it was with this funny parameterization. So we had this map P that goes from RP to RD, and empirical risk for the exponential loss. So this was, twice differentiable and L homogeneous. And for the gradient flow, and almost all data that's satisfies the following condition for that, if, and we had, the beta that we write here for almost all, just write it in here. Beta t here is this homogeneous function p of theta t. We'll write that as beta t. If this thing goes to 0, so this means that theta is going to diverging, but we want to know what happens in the situation where it converges in direction to something called theta infinity. That direction classifies things perfectly. So the min over I of yi p theta infinity transpose xi is strictly positive, and the gradient, the negative gradient for theta for beta t converges in direction to this. So if that, then we get this scaled version of theta infinity is a KKT point of this max margin problem for this data, which is the min of min over theta of the norm, such that you get a margin of at least 1. Yi p theta transpose xi is at least 1 for all I. So the KKT points, of course, satisfy this inequality, the equality and complementary slackness, that theta is equal to the transpose of the derivative of p times this sum across a subset of the i's, of these yi xi's, and the subset is the one which has yi, write it the same way, p theta transpose xi minus 1. So the subset of the non-zero alphas here is the ones where this constraint is met with equality. So the support vectors. Okay, so we saw that theorem statement last time. We want to see why that's true, or at least see a sketch of why that's true for the first part of today's lecture. And we were starting with this lemma that, so just to recap, that in the case where, we throw away the p theta, so this thing is just thinking about p theta is the identity function, then accumulation points of the negative gradient direction are going to be in this sort of direction. We can express them as a sum of these these yi xi's. Again, so for almost all data, blah, 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 the same kind of thing. If we have L hat of, let's call it theta t now, going to 0, theta t converging in direction. So theta t goes to infinity in the right direction. The direction that it converges to is theta infinity, and and that gamma, the min over I of yi theta infinity transpose xi is strictly greater than 0. Then any accumulation point of this set, let's say G infinity, of this set of directions of our negative gradient direction, theta t over that, any accumulation point can be written as a sum of alpha I times yi xi, where these are the ones that are the minimizers of this, right? Such that yi theta infinity transpose, write it as y, such that, yi theta infinity transpose xi is equal to, actually this quantity gamma. Okay, so we get this accumulation points necessarily can be expressed as a sum of these support vectors in this sort of a way. Okay, so let's see why that's true. This is really following the same sort of ideas as we saw when we were looking at gradient flow in the logistic regression setting, the over-parameterized logistic regression setting. So we're going to, just to fix some notation, this we'll call gamma I. So gamma is the smallest of these gamma i's. The set here of alphas, right? The I such that gamma I equals gamma. This is the I0 that we saw before. Let's call that S. I0 of the optimum point. And then, we're going to be interested in the min of the gamma i's that are not achieving, that are strictly bigger than gamma. So let's call that, nu is the min over I not in S of gamma I. Okay, so this is, greater than gamma. Okay, and now, we're just going to keep track of what happens with our theta. So we know that the loss is going to 0. So we can write, so we know theta is going to infinity, so we can write it as something times theta infinity plus an error term. There's a scale that's going to infinity plus some other thing, right? Some other function of time here, a vector value function of time that's dominated by dominated in magnitude by phi t. Okay, so and this thing is certainly going to infinity because our loss is going to infinity. And then we can just think about what happens to this gradient direction, or let's start with what happens to the gradient. of the empirical risk. This thing, of course, is just the sum of the e to the minus. Okay, I've dropped a whole lot of xi's, did I say? Great. So let's fix yi as 1 in the proof. Let's say proof sketch. We're not going to go through too much of this. So okay, let's set yi equal to 1. So we're replacing xi with yi xi. So this is an e to the minus xi transpose theta t. It's a negative, so we just get an xi here. And we can split that theta t up into this piece of growing magnitude and a piece of possibly growing magnitude but more slowly growing. Some other piece, some error term that's dominated by this one. Let's split that into the two pieces. This is over all I. We'll write it as a sum over I in the set and a sum outside the set, just as we saw before. All right, for the ones in the set, e to the minus xi transpose theta t, right? These have their gamma i's equal to gamma, so we get an e to the minus gamma times, for the theta infinity component of this, we get an e to the minus gamma times phi t. So let's put that out front here of whatever else we have, which is an e to the minus xi transpose rho t times xi, and then this other term is going to be an e to the minus. We'll write it in terms of the gamma I phi t. Rho t xi. Okay, and this is a combination of the xi's. We're going to see, this is just a scaling. We're going to see this is a scaling that applies to the whole thing. So let's define our alphas as these things. Call this alpha it. They're the coefficients of the x's. So we can write this term as x times some vector alpha. We're going to restrict ourselves to the subset of rows corresponding to S. We'll call that xs. And similarly, subset of components of alpha, I guess at time t. And then, we have this up here in the ... that was for almost all x. So generically, the guys that satisfy this equality constraint for almost all x, we have to have that set being smaller than D. We have to have this thing having full column rank. So when we think about our matrix here with full column rank times this vector, this combination of columns, must be at least as big as some constant times the norm of that vector. That's some data dependent constant. Okay, so let's, it's certainly going to depend on x, but we have this for almost all x, we can come up with some constant. So we get a lower bound on that quantity in terms of the norm on the scale of this thing in terms of the norm of alpha. So we're going to be able to, compare the scale of these two terms. The first term here has, the scale of this thing. Let's call this term AT and this term BT. And then we can I'm going to erase this part, and I think won't need much more than this space. So we'll leave the punchline up there. Okay, so the norm of this AT is at least as big as, so we have an e to the minus gamma phi t. And then we have this other, the norm of this thing is some data-dependent constant times the norm of alpha. So I'll write C, norm of alpha ST. This is at least as big as its minimum, I'm sorry, at least as big as any of its components. Let's take the max of those components. Alpha, remember, was e to the minus this thing. So we can put this inside. So this is at least as big as C times e to the minus gamma phi t plus whatever that thing was, minus xi transpose rho t. So we could write that as this thing is at least as big as its maximal component with a minus, that's the min over components of that vector of the xi transpose rho t. All right, and this is dominated by phi t. We know that much. So we could think of this as being just like e to the minus gamma phi t times a 1 plus epsilon, right? For suitably small epsilon and suitably large t. So for any epsilon and suitably any epsilon suitably large t, we can write it that way, right? This thing is compared to phi t. This ratio is going to 0, so we've got it drops below epsilon at some point. Similarly for the other term and this other term. So this one just has a different order of magnitude here, right? Because the gammas are strictly, we're outside the set, they're strictly bigger than the gamma i's are strictly bigger than gamma. All of them are bigger than nu, which is bigger than gamma. So, same argument says this thing is no more than something times, we're doing considering what happens across a bunch of these alphas, we can upper bound it by the max of those components times the number of those components, and we get an e to the minus. This constant doesn't hurt us at all. We get an e to the minus nu phi t for these guys. They're all bigger than this value, which is strictly bigger than gamma. And we get some other thing involving, these alphas, whatever. They're determined by the xi transpose rows down here. Same thing, this is never worse than a 1 minus epsilon down here. We get an upper bound because the rows compared to the phi's, will drop below epsilon at some point. So, we've got a comparison here. This gamma is bigger than nu. So for sufficiently large t, the ratio of these two things, b over a, is going to drop to 0. Is going to approach 0. It's going to drop below any value. Okay, for suitably small epsilon, I guess I should say, right? We've got to make sure that this thing, which is strictly bigger than gamma times 1 minus epsilon, is still strictly bigger than gamma times 1 plus epsilon, and then we win. Okay, so that's enough to show us that an accumulation point of the negative gradients, which is this thing, the negative gradient directions is an accumulation point of the dominant term here, appropriately normalized, the direction of that dominant term, which is precisely the result. Okay, and then we can apply that in proving this theorem. Maybe I'll pause for a moment. Very much the same argument as we saw in considering this gradient flow for logistic regression, but now we're arguing about what the accumulation points of our gradient directions, what direction they converge to. They're lying in this space spanned by the data corresponding to these support vectors. All right, and then to see why the theorem is true. Yeah, question.
Even though it doesn't make a difference for the proof, do we know that rho t? Do we only know that rho t is small in front of phi t, or do we know that it's like bounded?
That's good. In fact, we don't need to know either of those for the proof,
yeah.
Right? And for the theorem, we'll again be looking at kind of comparisons of the same things. So I guess in this setting, it's possible for rho t to grow in an unbounded way. Yeah. I mean, the answer is I don't know, but we don't need to. We're gonna always be doing a comparison of the two. Yeah. Okay, so let's think about the theorem. So proof, sketch, theorem. Okay, so we did this. So remember, P here is L homogeneous. So this scaling theta infinity down by gamma to the 1 over L means that theta infinity gives us a gamma as the minimum value. When we scale this down by gamma to the 1 over L, this is a L homogeneous function. So the scaled down version grows by that thing raised to the power L, so 1 over gamma, so the minimum is 1. Right, so we get this equality precisely. Right, so we know min first, min over I of yi p theta star transpose xi is 1. So that theta star is primal feasible. All right, so we're showing that theta star is a KKT point of this optimization problem. Feasibility is the first thing, and then we want to show we can express it in terms of this linear transformation of the sum of the alphas, the sum of the support vectors, weighted sum of the support vectors. Okay, and then we're going to think about what the argument to L hat looks like, what this beta t looks like. So let's, and we use homogeneity everywhere, right? So let's define beta infinity as the direction that we get from theta star, or equivalently theta infinity. All right, and then we can just use homogeneity to say, well then beta t is going to be converging in direction to beta infinity. All right, because we can put beta t is p of theta t divided by its norm. The theta t, you know, is this. So we could write scale the numerator and denominator by the same factor, which is the, you know, homogeneity tells us it's the same if we scale them down by their norms, and then we just get the you know, this thing as our ratio, and then we can just do a similar comparison to see what we get. Then we're going to be applying the lemma. We need to know that the beta infinity gives us a large margin solution. That's immediate. It's just a rescaling of the p theta infinity. So we can come up with this support vectors now for the betas, right, in terms of what those betas converge to, and work with the corresponding constraint set in our I've forgotten what we had as our dimensions in our beta space, right? So the d-dimensional space, and then the lemma tells us that, you know, the g infinity, the gradient of this thing the thing that this negative gradient direction converges to can be written as a sum over those alphas, for which, so let's write that out. G infinity here is a sum, we can write as a sum over I in the set S that came from the lemma of the yi xi's, with S being the things corresponding to the theta infinity. So this is the i's for which yi p theta infinity, or theta star equivalently, takes its minimal value. So in the case of theta star, that is 1. And then we can just write, you know, the various terms. So theta t, same idea. We can have, you know, it's scaling, it's going off to infinity in the direction of theta infinity, and there's some other little error term. We can write, let's squish this up a bit, plus epsilon theta t. We can write the negative gradient. This is just a gradient with respect to the argument here, the beta t argument of L hat. That thing we can write as some other function times g infinity, you know, and we know that's not going to infinity, but it's dominating the sum. We've got another error term. And then we can also consider the gradient of p at theta t. That's converging to in the direction of the gradient at theta infinity, and through homogeneity of L homogeneity of p, we know we have L minus 1 homogeneity of the derivative of p. So we can write this as you know, we get exactly the same rate here as we do for our theta, because we're wanting to scale this in the same way as we scale down theta. So we get a phi t to the L minus 1 times the derivative at that limiting direction, theta infinity, plus some error term here. So, you know, we're getting sort of the dominant terms in each case. And then, you know, we can just look at the gradient flow, theta t dot. the time derivative of our parameter, the argument for p, this high dimensional parameter, is just the derivative. This was the expression, p theta t transpose grad L hat beta t. And, you know, we can plug those terms in. So this thing looks like, somehow I've lost a minus sign. What do we have? So this is going to be phi t. Here's the dominant term for the derivative of p. There's an error term. The negative here becomes the dominant term of the, goes away in the definition of G infinity, and we get this dominant term plus an epsilon GT. And then we can, you know, just work with. So the whole game here is just arguing, you know, since everything's these bits are dominated by the dominant terms there, we can argue that the whole thing is dominated by just this product. We need to know that actually this vector dp theta infinity times g infinity is non-zero. But you know, that's again just a property of the homogeneity of p, because when because we can rewrite the derivative of p. So using this fact that the derivative of p at theta, we can rewrite its inner product with theta as degree of homogeneity times p. All right, and so we get something that looks like p times g, and we know that p times g, you know, is of this form, and that's a positive quantity because we have a positive margin for all these guys, right? So we've guaranteed from the form of from the homogeneity property actually that this vector is non-zero, and then you know, we know our loss is going to zero, so actually this product has to be going to infinity, and all these other terms are dominated by that product, and you know, we have a kind of ratio of things that one is definitely going to infinity, and the others, if they're going to infinity, then we have a kind of integral. We have to worry about integrals of terms. If they're both going to infinity, we can look at the derivatives, which are the integrands, and we know those ratios are going to zero, right? So all of the sort of other little stuff is dominated by this thing that's going to infinity, and so that's so we have that you know, theta t, the integral of this thing is converging in direction to this term, the dp theta infinity direction. Times g infinity divided by norm of that. And that ratio is what we call theta infinity. Theta star is a rescaling of that. You know, so we're getting that theta star is this dp theta infinity transpose times g infinity, which is what we wanted for the KKT point, because g infinity is of that exactly this form. But we needed to, you know, we're wanting this to be for theta star, not for theta star, not for theta infinity, so we can rescale the alphas, and it doesn't change this condition, of course. This is just a non-zero condition. So rescale the alphas appropriately to rescale theta, and the rescaling goes through here and so on, right? You can always shift them by the appropriate amount to get you know, exactly the solution to this equation. So we've shown that that this appropriately scaled theta infinity is for those alphas, or rescaled version of those alphas, is a KKT point of this max margin condition. Okay, so you know, so we've done gone to a lot of effort here to prove, you know, what is a kind of necessary condition. You can go to more effort to prove some additional properties that suggest we're finding a solution here, that actually the margin strictly increases under these sort of conditions. I mean, I guess I'm getting ahead of myself. Here we're assuming that we have things going to zero, and we're proving that we get a KKT point for this optimization problem. Before we go on to cases where working a little harder and actually proving convergence, I want to look at an example with this sort of homogeneous parametrization of linear functions. So a homogeneous parametrization of a logistic regression problem, because I want to see that actually, you know, changing the parametrization really changes what it means to find a solution to this problem, right? Really changes the nature of the asymptotic direction viewed as a linear logistic regression parameter to which you converge. Yeah. Yes. Of the, gamma L, I'm sorry. Where is, gamma to the 1 over L. Ah, okay. All we're doing here is rescaling things so that we get, so for theta star to be a KKT point of this optimization problem, we need to have theta star feasible, and we need to have a bunch of non-negative alphas that satisfy this condition for that theta star. So this rescaling is just to ensure that it's feasible, because we wanted a 1 here, right? All we had from theta infinity was there was some minimum value that was strictly positive. Things were separable. Let's call that value gamma and scale theta infinity back appropriately to ensure that the rescaled version has satisfies this condition, because the min of all of these values, with theta infinity in here, the min of these values is gamma. With theta infinity divided by gamma to the 1 over L, when we put that gamma to the 1 over L scaling through this L homogeneous function, we get the whole thing scaled by 1 over L, right? And then by 1 over gamma. And then this min of gamma becomes a min of 1, which is what we want for feasibility of the theta star. Sure. Okay, so let's look at an application of the theorem. You know, again, with this, wherever it is, this crazy parametrization of I don't know if I've written it anywhere. This crazy parametrization of our logistic regression problem, and we're going to look at specific homogeneous parametrization and see what impact we can observe in the direction to which, if things converge, the directions to which they converge. Okay, so this is I think a nice family of examples. So let's say lemma. So we're going to write, we have our parameters now which are theta 1, theta 2 to theta capital L. It's just a big vector, right? So this is in R, let's say D times L. Okay, so we have, we're in a d-dimensional logistic regression setting, and we're going to parameterize it in this crazy way. We're going to write it as, the beta here is going to be this function d of theta, which is take all of these guys and just multiply their components together, right? So do a kind of component-wise multiplication of these L vectors, and I've written that with a typo in the notes. These commute, so I've also done it in a bit of a funny order compared to what I did for other things, but that's fine. So it's the product of the diagonal matrix with theta 1 on the diag, same for theta 2, blah, 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 all the way up to theta L minus 1 times theta L. So we're just getting component-wise multiplication for that vector, okay? And then the lemma says, that. So now, okay, so this is, this map D is L homogeneous, right? It's just the product of L things in each component. It's sort of the trivial L homogeneous function. So, we certainly can apply this result, and we get, the min of the norm of that whole vector subject to this inequality constraint. So the lemma is just looking at that, for all beta in RD, the min of the norm that we see of the theta up here, so let's write theta as this concatenation, the min of that thing such that beta is equal to this L homogeneous function of theta is L times the 2 over L norm of beta raised to that power, right? So the sum of the components raised to the power 2 over L. Okay. So, so when we go and look at the min of the norm subject to this kind of constraint with that particular L homogeneous parameterization, that's the same as saying, so solution to star, i.e. Solution to star with P equal to D is, let's not say solution, let's say value of star is, it's an equivalent optimization problem to minimizing this thing, of course, right? Beta to the, raising the components to the power 2 over L and considering that sum such that for all I, yi, xi transpose beta is at least 1. All right, so we've turned our optimization problem. You remember in logistic regression, we got a 2 norm here. With this crazy parameterization, we're getting some other crazy norm appearing, right? So in particular, for instance, if we do just 2 of these, then this becomes a 1 norm, right? More of them, it becomes, some smaller power of the components of beta. So the parameterization really matters. Gradient flow is converging to the KKT points of these. The KKT points are really quite different with this different parameterization. Okay, and folks have investigated other kinds of parameterizations, things that are sort of motivated by convolutional neural nets, but in a linear setting. So again, something analogous to a logistic regression problem, but with one of these kind of bizarre, in that case, polynomial parameterizations. Yeah.
Is the conclusion to this result with this parameterization, is it like you're going to induce extreme sparsity in the betas for large L?
I was concluding something much more limited, just that the parameterization really matters. In this case, yeah, we're getting, as L grows, we're getting something that's encouraging sparser solutions. This is for something you might think of as a kind of weird linear neural net, right? Multiple layers of parameters, but no nonlinearities in there. But yeah, what that implies about the kinds of solutions you see for nonlinear parameterizations, much less clear. Yeah. And really, we know what the direction looks like, right? In terms of this optimization problem, it's just here's a case where we can easily understand the optimization problem's solution. Yeah, KKT points of that optimization problem. Okay, so let's have a look at why. I mean, this is a kind of easy calculation. Maybe we don't need to go through it in both directions. If you have a particular value of beta, then then finding the solution to given beta, if define theta star of beta as the solution of this optimization problem over here with P equal to D, then we can choose, I want to show an inequality in one direction, we can choose then here's a parameterization theta 1 for the ith guy. So the components of the first vector is going to be beta I to the 1 over L. The sign is in that first component, and theta, let's say ji, is just beta I to the 1 over L for j greater than 1. Then, clearly the product is this, computing this product, we get precisely beta. So d theta up here is equal to this beta. And then, so d theta is beta, and we get the norm, the value of that max margin optimization problem, the norm squared of theta at least, twice the value, I guess, is just, L times this kind of quantity. Okay, so we get an upper bound on the min over beta of this thing of that form, and you can go and compute a lower bound on that in the other direction, just using arithmetic mean, geometric mean comparison. So very simple argument for this expression. Okay, so this is a nice example that shows parameterization has a very significant impact on the implicit regularization that we see. Good point to pause. Any questions? Good. We're on track. Okay, so there are a bunch of criticisms that you could address at these results. We're assuming that we have convergence in direction. Okay, convergence to zero isn't that big a deal. Once you get, if you have a separable solution and you can find something that has small enough loss, then you can just scale things up, right? And the homogeneity is your friend. So in particular, once the empirical risk drops below a value that ensures that everybody's got the right sign, then certainly gradient flow is going to converge to the theta is going to diverge and the empirical risk is going to go to zero. Converging in direction, this is a much more unclear thing. So we do need some sort of conditions on our parameterization for that to be true. And it's a subtle question. So there's an example in the notes of a particular function for which, appropriately initialized, gradient flow is never going to converge in direction. You can define a function that's C infinity, the kind of profile in just 2 dimensions. The profile looks like this. It has something wacky going on out at radius 1. And you can set things up so that, start this thing off and, it will follow a nice parameterized path that has the radius going to 1. So everything stays in a compact set. The radius goes to 1. The direction just changes forever. You have a cycle, right? And you can look at the example in the notes. This is, the optimization folks have a very nice simple example that shows this. That even for a C infinity function, you can have crazy stuff happening, right? This is just spinning forever. So we need to. And this just uses very nice functions. It's sort of let's call it piecewise analytic, right? It's using exponential functions and a sinusoid, and it's the sinusoid that modulates things that has in its argument a rational function, and that rational function is going to infinity. So the angle just keeps spinning. The sine of the angle is going up and down forever. So we need to be careful about what kinds of parameterizations we work with, right? And your first thoughts about smoothness sort of properties, certainly are not sufficient. So we'll look at that. We'll impose some sort of reasonable conditions. This has been a theme. But with a very precise definition of reasonable that excludes, for instance, the sine function on all of the reals. Okay. The other thing that that I didn't, this was twice differentiable. The other thing I didn't really flag at the time, but and I'm surprised. I think I had one question come up about it. Differentiable and L homogeneous. This is pretty strong, right? Think of the ReLU case. It's certainly not differentiable. And if you want to make it differentiable and have that one homogeneity property, what are you left with? Right? It's a pretty limited class of functions that are going to be smooth to some extent and homogeneous. So that's actually a real issue. So we're going to look at actually, first of all, getting away from requiring smoothness. So we have to kind of work with non-smooth homogeneous parameterizations. We're going to define a class of reasonable parameterizations using the theory of O-minimality that's come out of model theory. That is enough to ensure that trajectories of a gradient flow on a compact set are always finite length. Okay, so this is very nice. So we get this sort of property out of that constraint on our parameterization. And then later we'll look at, actually homogeneity is itself a very strong condition because it's something that applies everywhere. And in fact, all we're concerned with in these results, right, is what happens as things get large, right, as parameters get large. And so we don't really care if we don't satisfy the homogeneity conditions for small values. We just want them to be satisfied as we go off to infinity. And there's an appropriate notion of near homogeneity that we can use there. So we'll see that as well. Yeah. I'm sorry, could you say that again? When does?
When is it L homogeneous in the infinite case?
In the infinite case.
Yeah.
When is it L homogeneous in the infinite case? I don't know what you mean by the infinite case. I'm sorry.
When t goes.
Oh, okay. So yeah, I'm being vague. There's a notion of near homogeneity. We'll define it precisely. It means that you may not have a homogeneous function in the sense of for every value of the argument, you have this scaling property. But once you get to sufficiently large values, you have a sufficiently good approximation to that scaling property. So it's really saying that the growth is the right polynomial asymptotically, and maybe it's not when the norm of the theta is too small, right? So that's what we mean by near homogeneity. We'll meet that later. Here we are talking about precise homogeneity that, for all theta and all positive scalings alpha, the function of alpha times theta is equal to alpha to the L times the function of theta, right? We'll meet a relaxation of that actually beginning of next lecture. Yeah. Any other questions?
Maybe it's not about homogeneity per se, but how do you deal with intercepts and this kind of
Intercepts.
yeah, and when you have a loss that might not be the variable xi multiplied by something, that you can have a translation of it.
Oh, right. Yes. So for instance, we argued that with ReLUs, with this piecewise linear function, that this thing is too homogeneous, right? And that this thing is 3 homogeneous. This is what you're talking about. And now what happens if, instead of actually being linear here, what happens if we have W1 x plus, B1, W2 plus B2, and so on. Is that what you're asking? Yeah. So absolutely. When we scale, I guess if we were at that point, we're still too homogeneous, but introduce this guy, scale him up, and everything scales up in a 1 homogeneous way, and for these guys it's a 2 homogeneous way, and we don't have 2 homogeneity anymore. So add in a very natural extra parameter, and the property goes away. Absolutely. And this is a big motivation. Turns out this is near homogeneous. This is near 3 homogeneous, right? Those betas only affect things when we're wanting to be precise. We actually, as we scale things up, we get very close to the right 3rd order polynomial growth. It's just not exact. Yeah. So this is, I think, later in the notes, a motivating example for near homogeneity. Yeah. All right. So let's look at. I'm really going to just, in some sense, expose you to the definitions and the results that we can give in these more or that have been found in these more general setting where we allow non-differentiability and where we impose conditions on the parametrization. And you know, both of those, as we've seen, are important. All right, so instead of working with derivatives, we're going to work with subdifferentials. So there's this notion of a Clark subdifferential. The Clark subdifferential of, you know, we need some sort of property. Locally Lipschitz is enough, so it's not differentiable, but differentiable almost everywhere. So the Clark subdifferential of a locally Lipschitz f at a point is, and we'll use this partial notation, df of x. It's the convex hull of the kind of limiting directions. Since this is locally Lipschitz, we can always find a sequence of points that converge to x where the gradient is defined. All right, so that the xi is in our set. So I guess f maps from, you know, we're always going to be working in, let's say, RD, where the xi are in x, the xi converge to x, and the gradient at xi exists. Okay, so this is well defined. It's non-empty. It's convex. This means convex hull of the set of limiting gradients, right? And it's a compact set, and that means that we can define the min norm subgradient. Which we write as, with a bar here, is the argmin argmin of the norm of a y in that Clark subdifferential of f at x. Of y. Okay, and when the gradient exists at the point x, you know, this is just that point, and so this is just the gradient, right? It's a natural generalization of that. We're going to be interested in, you know, our gradient flow that has these nice properties that it decreases the empirical risk, and for that, you know, we need to be a little careful about the kinds of paths that we consider. So, okay, so let's say that you know, we consider an arc. So we're thinking about a gradient flow, say, as a function of time. So this is a theta from r plus to rd, I guess. Is an arc, and by this we mean it's absolutely continuous. So we can find a y, you know, there exists a y that has for which we can express theta t as the, you know, there's a kind of time derivative y for our theta, 0 to t. That's, you know, integrable on any compact interval, and we say that f admits a chain rule, and f for which we can define the Clark differential. So a locally Lipschitz f admits a chain rule, if we have the kind of derivative with respect to time of f of theta t having the right chain rule kind of property. So if for any arc theta and any element of the Clark differential of f at our theta t at some point on this arc, and almost all t, that the time derivative of f of theta t behaves the way we'd like it to, is equal to the inner product between this element of the Clark differential and the time derivative of theta. All right, so you know, quite generally, you can get a chain rule with Clark subdifferentials, but it's in terms of it's an inclusion result, right? Saying that the Clark subdifferential of a composition is contained in the kind of appropriate product of Clark subdifferentials, right? But we want something stronger than that. We want to be able to say that when we run our gradient flow, so our gradient flow is an arc. So gradient flow is an arc theta that satisfies theta t is in the negative differential of L hat of theta t. And we like that, that our gradient flow has this nice property that the derivative with respect to time of our empirical risk we can write as equal to the negative of the this thing, and you know, this satisfies. So if we have, this implies if we have that our L hat admits a chain rule, then gradient flow is going to satisfy for almost all t. The derivative is this negative norm squared of theta dot. Lost my dot. Okay, so that's going to be important. And you know, it turns out this is a consequence of this O minimality property, this reasonableness property that we're going to impose on our parameterization and on our loss, I guess, right? So the empirical risk as a function of theta. So all of these things, this sort of chain of calculations from parameters to empirical risk need to satisfy some sort of a restriction. Okay, and the restriction, you know, there's this nice notion from model theory in logic that gives us a kind of family of functions that we can work with that are enough to ensure, you know, nice properties of the gradient flow, enough to ensure that you know, we don't have any of this bizarre kind of space filling curves as our trajectories, and we can get convergence in direction when our empirical risk is going to zero, for instance, in this exponential or logistic kind of case. Yeah.
So this Clark
Subdifferential, yeah.
so how do we call this?
Which one? This.
The convex hull space.
This one. This is the convex hull of. No.
This is the left hand side. How do we call this?
I'm going to say the Clark subdifferential.
Okay.
You know, you can call it partial f or something.
So
Yeah.
just for intuition, if the graph is
Speak
continuous,
later.
essentially this will be a single point.
That's right. The convex hull of this point.
Points that this graph converges, then we take, I don't know, a triangle or the convex hull essentially.
That's right. It's the convex hull of the set of gradients that. So, for instance, you know, when you think about the ReLU at this point, right? Its derivative over here is +1. Its derivative here is 0. Its derivative at that point is the interval, right? The convex hull of 0 and 1. Yeah. You know, similarly, if you've got these points of non-differentiability or let's say lines of non-differentiability in some higher dimensional setting, it's the convex hull of everything that we can see locally. Yeah.
Is it for the exponential loss?
Great. So here I'm just talking about a general loss, but we're going to have to impose. But I'm writing it as, you know, an empirical risk as a function of parameters. So there's, you know, our parameterized function class, and there's our loss that goes into that, and you know, there's averaging over the sample as well, right? So there are sort of all these pieces, and we'll see, you know, we need to restrict everything that goes into the kind of. Essentially, you can view this as a sort of computational model, and as long as you stick to that model of computation that takes you from parameters all the way to empirical risk, then we're good, and we're going to be able to satisfy, you know, this nice property for gradient flow and various other things, right? So so we have to be careful about that full chain from theta to empirical risk. Yeah. So, you know, so yes, we want to include exponential. And actually, you know, this was a big advance in model theory to come up with what's called an O minimal structure. That includes the exponential function. Okay, so it's a sequence. You can think of it as, I guess, let's talk about an O minimal structure, and then there are definable functions that we can define in terms of this. So an O minimal structure is a sequence of sets of subsets. Each one is a subset of the power set, so the set of subsets of Rn for Sn. So we're thinking about the sorts of sets that we're allowed to deal with, right? So Sn is a set of subsets of Rn. And, you know, you can do all of the, so a kind of, let's say, minimal O minimal structure is kind of all of the semi-algebraic sets, right? So if you think about S1 contains, but it can be bigger than that, right? And actually the interesting case is bigger than that. So it contains all open intervals. This is a set of subsets of R, right? We need to have, you know, some other properties. Okay, zero sets. Sn contains zero sets of polynomials. You know, on Rn. Sn is closed. We need a bunch of closure properties. Closed under finite unions, finite intersections, and complements. Finite intersections and complements. We have, and then we have closure properties among these different values of n. So we've got to have the whole thing being closed under projections. Let's just say Cartesian products and projections, which is enough to equivalent to what I wrote there. Maybe we'll say axis projections, coordinate projections. So this is the set of conditions defining O minimality, and then we talk about functions. So a set is definable if it's contained in any of these SNs, and it's a function is definable. I'm struggling to write down here. If its graph is in, Sn for some appropriate n, right? Or maybe I'll write whatever. Depends on the range and domain of f, right? Okay, so this is a constraint. Turns out it's not such a strong constraint for what we want to do. Where and that's because of this result from the mid-90s. Wilkie showed that there's an O minimal structure for which the exponential function is definable. All right, so you can come up with an appropriate sets for which that's true. That its graph is in S2, and that's enough. With all these other conditions, to include all of the examples that we've seen so far of things you can compute with neural nets. We can do exponentials. We can do all the appropriate, taking a max to compute a ReLU. We can do logistic loss and things of this sort, right? Exponential loss, all of those things. An O minimal structure is rich enough to do all of the things that we've talked about. It's not totally general. For instance, the sinusoid on the reals is not definable in an O minimal structure. Okay, and this example, I guess one way to see that is this kind of property that it doesn't converge in direction. You have on a compact set, you've got the gradient flow for that function that includes all these other pieces that do fit in are definable in an O minimal structure, but we have a sine function there, and what breaks down is that sine function. It's a solution to a second order differential equation. Turns out first order differential equations. So this Wilkie result was more general. It's for things that are solutions to first order differential equations. That's also good enough here. Okay, so we have to be restricted to reasonable functions, and that's what this definition suffices as a notion of reasonableness here. It's something that's appeared in statistical learning theory in other contexts. Soon after Wilkie's result, people were trying to prove bounds on the VC dimension for neural nets with sigmoid functions. And that exponential was really problematic, and you could come up with similar counterexamples to the sort of sinusoid thing that oscillates under a gradient flow. In that case, you could get arbitrarily fine-grained behavior by kind of burying a sinusoid in a sigmoid to say, look, the VC dimension is necessarily infinite for a single parameter. So it was, you needed to have restrictions in that setting as well, and it turned out this was I was going to say right. This was a sufficient notion of reasonableness in that context, and led to a solution to that problem. I gave a little bit of a blurb in the notes about some of these notions of VC dimension and VC density. Okay, and then the key property that's that follows from this sort of restriction, and I'm not going to prove this, is that if we have that all of the things we're concerned with, Clark subdifferentials and minimum norm subgradients are definable, and when we think about when we start with a locally Lipschitz definable function, they're definable, and we get that this thing admits a chain rule. So maybe I'll write down a summary at least of that so there's this result that F definable implies that these Clark subdifferentials, the minimum norm subdifferential is definable. Both of these are definable in our family. That F, this is for where this definition makes sense. So locally Lipschitz F, then F admits a chain rule. In this sense. And if you have a gradient flow of this form over here, this kind of a thing, where our empirical risk is definable and locally Lipschitz, so the definition of the gradient flow makes sense, then you have, for almost all t, we have this nice property, right? And I guess we also have that the theta dot for almost all t. Yeah, I guess theta dot is actually equal to the minimum norm subdifferential. Okay, so these are consequences of this notion of reasonableness, and then there's a result. So I'll cut that off. And then there's a result. This is a combination of two results. Let me double check that I'm getting things right. Right, so I think the first one was Kaifeng, Liu, and Jian Li from 2019. So they proved a kind of conditional result that said if you have convergence, then you get the sort of properties that we're seeing. And then subsequently, Jiwei, Ji, and Matus Telgarsky, and I think this is 2020. I've got to check that too. Showed that this follows, right. 2020 showed that that the convergence conditions follow from the O minimality, from definability properties. Okay, so for the theorem is again for gradient flow on L hat. Hat denote the blah blah blah. Right, gradient flow on this thing. L hat of theta is the empirical risk for the exponential loss for a parametrized class theta xi. It looks like this. this f needs to be locally Lipschitz, definable in an O-minimal structure that admits the exponential function. And locally Lipschitz. And our gradient flow is this an arc that satisfies this condition over here. Then they say for that, if L hat gets below some value at time t naught, and that value is small enough that every data point is classified correctly. So how we get there, is not the subject of the theorem. Blah, blah, blah. Then we converge to 0. So L hat theta t converges to 0. The theta t goes to infinity. In fact, we know the rate. It grows appropriate as a polylog kind of function of time. It converges in direction. Yeah, so I should say plus for these two because I'm combining results from two papers here. This thing converges in direction to theta infinity, to some theta infinity. And we can write theta infinity as the aligned with, so and I guess there exists a scaling, what did I call it, C, so that when we scale theta infinity by C, it satisfies the KKT conditions of our max margin condition, min of theta squared such that yi f of theta xi is at least 1. Okay, and the KKT conditions, in this non-differentiable case, they're just what you would expect. We're working with these subdifferentials instead of with the gradients, and so we have an inclusion there rather than an equality. Yeah. This condition being smaller than 1 over n means that this thing, what do we have? That every one of these has to have this exponential smaller than 1, which means we've got our f theta xi to the right side of 0. That's right. So we're already at time t0 classifying our data correctly, and we're only talking about the asymptotics. Yeah, what happens as we then drive the empirical risk to 0?
But if we predict well from the start, we don't have to do a gradient descent.
If we predict well, so here we're looking at what kind of properties gradient flow has when we are minimizing a criterion like this, right? So in this kind of generality, when we're just talking about a parameterized function of theta, it's very hard to say anything about what a local algorithm like gradient flow is going to do. Whether it'll get stuck in some local optimum at some stationary point or whatever. here we're wanting to know, assuming all goes well, in the overparameterized setting where, there's, this is really rather arbitrary, right? The definition we have for F. We just need, I've omitted a homogeneity condition somewhere. So I guess I should have written that in here. Not quite as arbitrary. But yes, we need this. So not even clear that that if there is, it's not even clear that we can classify everything correctly. But what we're saying here is, if we're in that situation, then what is the asymptotics? What does that look like, right? What's the solution that we go to as t goes to infinity? You're absolutely right. Like it's under a strong condition on the behavior of the gradient flow up to the point t0. Yeah. On the other hand, we can't hope for better under such a general case. We're kind of looking at the second phase there, right? After we've magically got to a good point that classifies everything correctly. Then what?
For the first limit, we start from definable, right? But for the class
And locally Lipschitz, yeah.
That's all the conditions.
Yeah. Yes.
There is not a way to derive local ellipses from.
No. We need locally Lipschitz. The definition of the Clark subdifferential required things to be differentiable almost everywhere. Yeah.
So, but if I understood correctly, the Clark differential is a set, right? So for any point x, the Clark differential is a set.
That's a set, and this is the minimum norm element of that set.
So for that set, I guess it's the notion of definability has to be understood in terms of like the graph of this multivariate function, right?
Right. I mean, I didn't write it here. So a set is definable. This means if a set A is definable if A is an element of the union of these SNs, right? So I'm sort of using a shorthand notation, yeah. Right? So this is definable and the graph of this function is definable. Yeah.
Could you just clarify what is restrictive exactly in the definition of omnimal structure? In the sense that why couldn't we use just a P of Rn?
A T of R.
P of
Oh, P of Rn. Okay. We need to let's see where we are. I'm a bit lost.
I guess you're trying to exclude the exponential function, right? So that's it. I guess you're searching for a... Yeah.
So what's the sort of, why is it limited? Why can't we every function?
Because I assume this should restrict something. Like we should exclude
Yes.
some parts of Rn. But all of this is just like minimal
Yes.
objects that it has to contain. But
Yes.
it doesn't say,
Yeah, absolutely. So my definition is lacking. So let me, but I'm already over time, and I'm sorry, I just noticed that. Let me fix that at the beginning of the next lecture. Yeah, I do apologize. And
At the end of the day, what you exclude in the original sets is the kind of set, like the zero set of the sign function. This is why it's not defined.
yeah, yeah.
It's discrete and infinite, so it's not defining. This is typically the stuff that you're excluding.
These are exactly the things that you're excluding, but my definition is broken. So let me fix that next time. And I'm sorry, I didn't even notice I'd gone over time. Yeah. Any quick questions? And yeah. I'm sorry?
If you have a L2 regularization on the theta, then what would
Then we can't diverge, right? Then we have a strongly convex loss, and we certainly won't go to infinity, and there'll be, this is much more classical. It's converges to there's a compact set, and you can look at, for instance, the homogeneity properties of F to argue about the scale of that compact set always, yeah. Is that what you're asking in the regularized case? Yeah. So, very different, but here we're driving the loss to zero and interested in the properties of that solution. Yeah. I should stop there. I'm 5 minutes late.